Assalamu alaikum, ladies and gentlemen, welcome back to another live stream. This stream would be quite interesting. I've never made an OS before and I haven't even read the tutorial yet. Maybe just the first bits and that's it. I just skimmed through it, like skimmed through the first part. Other than that, we're gonna be doing this live pretty much, and please, you're welcome to my server so you can get notified. You can vote for new streams and all sorts of cool stuff. Anyways, alrighty. Okay, good. Okay, let's go ahead and start. So I'm gonna be following through this guide, and in fact there is multiple parts, or not parts, there's multiple versions of this guide. There's the old version and there's the second version, which is the one that we're gonna be following today. I haven't read through the old version, but yeah, I mean, since I'm starting now and the second version is on, so I'm gonna follow the second version of this guide basically. So let's get started pretty much. All right, let me make sure all the stream is good to go. Mic is on, great. Seems good to me. Anyways, all right, let's start our project, I think. So the vlog series creates a small operating system in the Rust programming language. Each post is a small tutorial and includes all needed code, so you can follow along if you like. The source code is also available in the corresponding GitHub repository. And in fact, the repo, I've checked it out, it's pretty active. So just yesterday is the last commit, which is interesting. So that's great. Anyways, let's get into it pretty much. So let's start by a freestanding Rust binary. I've never made a freestanding Rust binary before. I'm gonna try to not read through the whole thing, otherwise the stream would be so boring. But I would read if I can't figure it out. Anyways, we'll see how it goes. So, cargo new, okay, I can do that. Cargo new, Kodachaku OS, I guess. And let's go. Cargo cd Kodachaku OS. Great, let's open up code here. Let's close this guy. And there you go. Okay, main.rs. Alright. As always, allow in use, correct, and allow that code. And forbid in use, must use, so the Rust analyzer is less annoying. But yeah, okay, great. So let's go to the first steps, I guess. Alright, so we have made a binary right now. Great. So the first step, since we're not gonna have any operating system, which means we're not gonna have any standard library, so we shouldn't include the standard library, so we're gonna add this to here, no std. And so you're gonna notice right away that we cannot use print line, vic, etc. All that cool stuff, we cannot use it anymore. We have to do everything ourselves. So no standard library, basically get rid of the Rust standard library and also get rid of the libc, right? So the standard library of C, which is being used basically by every single language out there. Yeah, anyways, okay, let's try to build. Cargo B. Okay, so the first error that we get is panic handler function required but not found. In winding, panics are not supported without std, as you can see. So since we have disabled standard library, we have to make our own panic handler. Since like usually with the standard library, you would basically get the panic handler in the runtime of Rust. So in fact, all languages have runtimes, well, at least almost all of them. Unless if you're working with assembly directly and not using a runtime, I guess, so libc and stuff like that. But basically, you know, the difference between, let's say, a C# runtime and Rust's runtime, or C++ runtime, or C runtime, is that it's not a, you know, it's very lightweight, nothing crazy. It doesn't do much for you. It, like, for example, what it could do is basically it have some logic, that calls into your main function, that hooks into the start label in assembly and such crazy stuff. It also handles panics. When your code panics, it handles the unwinding of that panics and the stack, initialize the stack, etc. At least that's what I understand until now as a noob. Okay, from my modest knowledge, right? Okay, cool. So basically, I'm gonna need some function call with the panic as a panic handler, since I don't have one anymore. Okay, so the AI is already helping me here. Interesting. Okay, found duplicate length item. A panic and pull that length item is first defined and create a std which says depend on first definition is std located from. Okay, interesting. I think because we have tests on, and maybe tests are basically using the standard library and somehow it's clashing. So, interesting. How to disable tests in Rust. Another option is add to ignore. No, that's not what I want. I think I've seen a comment somewhere that talked about such an issue, I believe. Let me see. Because I haven't gone through this yet. This is my first time going through this, pretty much. But I have looked through the comments. Yeah, someone had, yeah, there you go. Someone had the same issue as me here. And then need to read the error and do the step with the help Rust target add. Yeah, I think maybe it's gonna be fixed later on. I'm going over myself right now. Anyways, let's see. So basically the same thing as I've done here. Cool. And this language item is called personality. Yeah. Basically stands for exception handling or error handling. So yeah, abort on panic. And personality because that it controls the behavior of that exception handling mechanism. Let's try to disable unwind in here. Cargo terminal. Oops. Oh, what the? Oh, I see. Sometimes the mic cord gets in the way of my control key because I have a mechanical keyboard, and that happens. Anyways, let's get going. Okay, cool. So I've removed that. And what if I remove this one too now after doing that? Function required. Well, it is required after all. But now I don't get that error anymore, it seems like. Now, using fn main requires a standard library. Use no main to bypass the Rust generated entry point. Declare platform specific entry point yourself, usually with no mangle. Interesting. So I guess maybe I would put no main here. And okay, link fatal error entry point must be defined. Interesting. So let's try to declare extern start. Hello Hads, welcome to the live stream. How is it going? Welcome back. Oh, extern C, I think. Expected, oh my bad, fn. Does that help? No mangle, yeah. I don't know if that helps. No. Let's see the other stuff. Okay. Overwriting the entry point. Pub extern C fn start. I've gone through a bit of assembly. I know some assembly, and we actually use this label start as where basically the label that the program starts in, that's the label that your operating system calls. But hold on, we don't have operating system right now. We're making one. Interesting. Yeah, that's the job of the bootloader at that point, right? So anyways, linker errors. building for bare metal. And you're gonna ask how the bootloader then does it. Well, it basically uses some assembly, at least that's what I remember. And like you have to do something with 4 kilobytes or some weird. Oh, pub, yeah, good catch, good catch. So it has to do with some assembly, so like 4 kilobytes or something. So basically the CPU looks into is it the disk or what exactly? But yeah, it looks into some specific address and starts from there essentially, and that's where the your bootloader should exist, right? And then the bootloader takes it from there to actually boot your operating system. So fatal error entry point must be defined. Okay. All right. What's next? What's next? Rust up target add. So this is basically, as you notice here, this is a host, or like not host, target triple. So basically it contains here the what is it called? But basically none meaning no operating system, right? And I think this is basically a Arch architecture. Well, embedded ARM. Embedded ARM, right? System. There you go. Anyways, I don't know if I want to go with this path because there is another path that we could do, which is linker arguments. And looking from the comments, I think we're gonna need this anyway at some point. It depends if it is MBR or UFI. If it is MBR, is the first 500 bytes or so. If UFI is more flexible, IG. Not sure. The BIOS loads both though. Yeah, that seems about right. I do know a bit of knowledge about UFI and MBR and all that crazy stuff, thanks to installing Linux from scratch, Arch Linux from scratch. Other than that, not much. So, anyways, let's go to the next one. So you're supposed to, I think, cargo rust C. You could pass in this linker arguments. Or otherwise, the better way, in my opinion, I think it's probably using the config toml here. So .cargo/config.toml. Okay. I'm not sure if this would work or we still need that other step, but let's try it. I would guess we only need this one, but let's see. Cargo slash oopsies, not that. Hold on. Let's remove this. How to remove it? Delete. Okay. So .cargo. Well, not really in src. Outside of it. Okay, cool. .cargo/cargo.toml. Or is it? I think so. Well, config toml. Oh my god. We're starting great here. config.toml. Hello. What should I call you, by the way? How do you spell your name? What's up? How's it going? Welcome to the stream. Welcome back. What should I call you? Robert? Oh, I see. I just remember right now. Welcome, Robert. Okay, so what the heck is going on? Oh, crap. It actually, I guess it didn't make a file. Bruh. Well, delete this. I guess I'm just gonna do it the old way. Just do it like that. config.toml. And there you go. Okay, cool. So if it's Linux, we're gonna pass these link arguments, and if it's Windows, we're gonna pass these. If it's Mac OS, we're gonna pass these for building. Of course, this is not for the actual OS, right? Our OS could run on any architecture we support. But this is just so we can actually build it on our operating system. Is that Cyrillic alphabet? Oh, I see. Okay. No, it's Russian. Interesting. Static link. So why that's the case? Because, well, of course we have separate, like, different linkers depending on the operating system. So yeah, let's see how this would work by any chance. Okay, it actually worked right now. But it's still saying to me found duplicate link item. Should I maybe... Hopefully there's a way to fix it. Restart the server. Okay, let's see if restarting the server would fix it. because otherwise that would be annoying. Yeah, it seems to have fixed it, I think. There you go. Cool. So right now we're officially building, I think, our own free, what is it called again? Freestanding Rust binary. Let's see how small it is. Hold on a second. Let's see how small it is. Where's my target? Okay, cool. Let's open it and reveal File Explorer. Target, debug. So the debug build is 1.5 kilobyte. What if we build for release? Oh, sorry. -- release. Okay, what about the release? Come on. Oh, maybe it crashed right? It called the panic right now or something? Because it seems to maybe have looped. Yeah, anyways. No rationality uses small subset of the Cyrillic alphabet, 80% market share by next year. Okay, let's see what we got now. So where is it? Target, release. It's actually the same as the release, right? 1.5 kilobyte. Okay. Oh yeah, my bad. It actually hangs because right now our start function cannot return because there's nowhere to return, right? So we have this type right here, meaning no return, and we're supposed to actually call the exit function of the what should I call it? Maybe the halt instruction of the CPU, I think. But right now we're just making the loop for now as a temporary solution, right? So we don't return. We never return like this. That's great. Where can I get my copy of this operating system? The year of code attack. Use cargo R instead of cargo B, so the binary was. Oh yeah, that makes sense, right? And welcome to the stream, Jezza. Welcome. This is quite annoying, by the way. Found duplicate link items. So the Rust server have this problem. Let me see. Let me see if we can find a solution. Otherwise, this is very annoying. Rust analyzer. No, I don't have to restart my editor. I just restarted the Rust analyzer and it fixed it for a while, but after that it just didn't work anymore. So that sucks. Okay, I think it's, yeah, exactly, it's following the same guide. Create a node, CDA must specify. Believes there is an error, shows it. Yeah. It's coming from us. See what's the result if you run cargo check. Oh. What if I run cargo check? Good question. Nothing. It's fine. Added custom target and deployed cargo config to B. Find target as follows. Displays this error. Oh. A bit confused. Where is this check on save attribute? Can I do a sperm? Open workspace settings or VS Code for workspace settings. I'm not on VS Code. I'm using Cock Rust analyze this and ID specific thing. You're using NeoVim. Yes. Okay, let's try, I guess, maybe that solution, or maybe we could check E for another. CFG not test? Really? Is then grayed out within VS Code. Okay, let's try this one. And then it's grayed out. CFG not test. Interesting. Maybe that works. I don't know. Maybe that works. There's also the other solution that we found here, which was this. I think you can change check on save setting, for example, for Rust C development. So check on save. Back to lobby. Welcome to live stream. You're making an OS. Time to switch from Windows. That early? You can check the check on save setting, for example. So here they're running some x.py check JSON output. In your case, maybe something like this would work. Cargo x check, but it's not like saying how that works. But I mean, we could try it. There is no problem in that, I guess. We're expecting Kodotaku OS to have 80% market share by next. Alright. Okay, so where we should do this? Workspace settings, JSON. Okay, so would this help by any chance? Oh, Rust Analyzer have a warning. Cargo check failed to start. Failed to run the following command. Cannot find this file specified. Interesting. So it failed to run this. So yeah, that doesn't seem to work out so well. Okay, anyways, let's just keep this one for now. That seems good to me. Anyways, so we got that binary that we wanted. Let's go to the next step, I think. Summary. So don't link the Rust standard library. Disable all Rust level entry points. Don't mangle the name of this function. Yeah, because Rust functions and even C++ functions, for example, do some mangling for the function names. So they support some other stuff. I think maybe like generics and stuff like that. But for C, so the linker can call directly into this function, it have to have the same name, otherwise it wouldn't work, of course. So looks for, there you go, named star by default. This function is called on panic. Okay, and we also do profile.div panic, right? Cargo toml profile.div panic equal abort. So we just terminate the process when a panic happens instead of calling the panic handler. Okay, disable stack in winding on panic. Okay, cool. And that's pretty much it for that one. Let's go to a minimal Rust kernel. Okay. Alright, I guess I'm just gonna glimpse through this for now. And I haven't read this yet, but we'll see. For a target system, I will require some special configuration parameters. File unfortunate Rust allows us to define our own target through a JSON file. So you can actually make your own Rust target through just a JSON file. Interesting. Most fields are required by LLVM to generate code for the platform. For example, the data layout field. We also target x86-64 systems with our kernel. Will look very similar. With the common content. Note that we changed the OS and alright. Interesting. So I think this, yeah, putting it all together now looks like this. But the real question right now is, where can I put this? I think he said something about the name somewhere around here. Okay, so but where should we put it? I have no clue. Anyways, we're gonna call it x86-64-myOS. I don't know where to put it, but let's say x86-64 Kodotaku OS, I think, .json. So LLVM target, data layout, I have no clue what that is. I should check on it. Arch or architecture, target Indian lil, target pointer width, target cint width, OS none, executables true, link flavor LD linker, and Rust LD, panic strategy abort, disable red zone true. I think after we actually use this target, we probably wouldn't need those panic handler stuff anymore. But we'll see. plus soft dash float. Okay, so how can I right now use this target? Compiler for our new target will use Linux conventions. I'm not quite sure why. I assume it's just LVM's default. This means that we need an entry point named star as described in the previous post. Wait, I already did this, right? Yeah. Oh, there you go. So cargo build dash dash target, and you just pass it the JSON file. Interesting. Magic. So a target is just a JSON file after all. At least in Rust. I don't know what it takes to do the same in other languages. Hopefully it's not a nightmare. Dash dash target. Oops. X80. Okay, so the file. Is it exactly what I'm calling it? No, not exactly. Hold on a second. Just to keep the I don't think the name matters, but I'd like to keep the convention straight. Kodataku. Let's just go that way. Okay, cool. X86. Can't find crate. Huh. Can't find crate for core. What are you talking about? Here. It's talking about here. Oh yeah, there you go. Can't find crates for core. It fails. The error tells us that the Rust compiler no longer finds the core library. Oh crap. This library contains basic Rust types such as result option and iterators. Okay. Oh my god. So the core library is distributed together with the Rust compiler as a pre-compiled library, so it's only valid for supported host triples, but not for a custom target. So I guess we're gonna compile ourselves. Oh crap. Okay. That's where the build. Hello Theo Paris, welcome to the live stream. Our admin is here. Welcome, welcome. Okay. That's where the build std feature of cargo comes in. It allows to recompile core. Okay, I thought we're gonna legit go commit, like basically clone the compiler repo, you know, the Rust source code, then recompile core ourselves. That would have been great. This feature is very new and still not finished, so it's marked as unstable, only available on nightly Rust compilers. Yeah, I am actually using nightly Rust. And just to make sure I don't forget, I'm gonna actually make a Rust that toolchain toml. Basically, when I'm gonna upload this into GitHub, you know, so whoever wants to run this, they would hopefully just be able to like directly say cargo B and it would work without having to, you know, go crazy with targets and arguments and so on. So I forgot how does this work. Let me see if the AI can help real quick. Well, I don't think he can. Let's just go and look for the search engine then. Toolchain toml. I can never remember this stuff. Let's see. Come on, come on, come on. Okay, so toolchain channel nightly. I'm just gonna go with nightly. I don't have a specific nightly build for now. And so anyone who gets this repo and compile it, it would make sure that the toolchain is correct, pretty much. So that's great. Okay, what else we need? In cargo config toml, and stable build std core compiler built in. Cargo config toml, okay. So in stable build std core compiler built in. So is that enough? Okay, we're building the compiler core library ourselves. That is cool, man. I didn't think it was gonna be this easy. That's great. We have fixed it. There you go. Cool. By the way, right now we're actually need to do it like this, cargo b dash dash target, because I think without this it wouldn't really work, right? Yes, it wouldn't work. So let's make sure to hopefully put it into this cargo config toml somehow. Let me check out the documentation for this. There you go, and maybe we can find something that helps here. Oh, there you go. So build target. Do we have a build here? Doesn't seem like. So maybe I could add it. And target is equal to, and maybe use our own thing. Would that work by any chance? No clue. Never tried this in my life. Let's try now cargo B. There you go. It works. Let's go. Let's go, man. That's lovely. You could actually juggle all of these arguments here, which is very cool stuff. Love this. Anyways, let's go back to our stuff right now. Build dash scd and build dash scd features. Compiler built-ins mem. Why we need this though? Hold on. So fortunately the compiler built-ins crate already contains implementation for all the needed functions. They are just disabled by default to not collide with the implementation from the C library. We can enable them by setting cargo's build scd features flag to compiler built-ins mem. Like the build scd flag, this flag can be either passed on the command line as a -z flag or configured in the unstable table. Okay. Unstable. I've just realized that. Anyways, table in the cargo config toml file. Since we always want to build with this flag, the config file option makes more sense for us. Okay, cool. And what was the... So the Rust compiler assumes there is a certain set of built-in functions available for all system modes. These functions are provided by the compiler built-ins crate that we just recompiled. However, there are some memory-related functions in that crate that are not enabled by default because they are normally provided by the C library on the system. So that's why Rust links libc by default. Okay, these functions include memset. Okay, which sets all bytes in a memory block to a given value. Memcopy, which copies one memory block to another, and memcmp, which compares two memory blocks. While we didn't need any of these functions to compile our kernel right now, they will be required as soon as we add some more code to it when copying structs around. Interesting. By the way, I have some funny moments with. So like I have a hate relationship with the C standard library. So I was trying to re-implement memset and memcopy and all of these cool functions, right? And I used the same name and some weird stuff happened. Apparently you don't want to do that. If you want to re-implement your own functions like this, don't use the same name because the compiler do some stuff with it. But anyways, with this change, our kernel has valid implementation for all compiler required functions, so it will continue to compile even if our code gets more complex. So behind the scenes, this flag enables the mem feature, the compiler built-in crate, the effect that the no mingle attributes applied to the mem copies that are implemented in the crate, which makes them available to the linker. Okay, gotcha. So cool. Alright, so does that work? Okay, we're compiling that. Great, so everything works until now. And now we set it. Oh yeah, we have already done this. Okay, print it to the screen. Okay, we're actually going to be printing to the screen now. Crazy. So the easiest way to print text to the screen in this is the VGA text buffer. It is a special memory area mapped to the VGA hardware that contains the content displayed on screen. It normally consists of 25 lines that each contain 80 character cells. Each character cell displays an ASCII character with some foreground. The background colors and screen output looks like this. Okay, so we're going to use the BIOS, I think, to print some characters right now. By basically changing the VGA buffer. Okay, we will discuss the exact. So that's basically how Spartan programmers were programming back in the day. Like, instead of actually doing system calls and all that crazy stuff, you didn't have an OS. You would just go right into some system, like some predefined memory address, depending on the hardware. You would find it in the hardware manual, or you would find it even as a preprocessor macro in like for assembly from the manufacturer of the hardware, right? So, and you would just use that in your assembly code. And you just like poke memory directly and stuff would happen basically. So like, for example, for drawing sprites, you would just go ahead, poke some memory address, and there you go, you got a sprite on your screen. It was very easy. But anyways, for I, byte in hello, iterate, enumerate, and save VGA buffer offset. Okay, we're in safe territory right now. So this is our loop right now. Okay, so let's go. So we have a static variable here, or static constant, should I say. Can't find crate for chest. What the heck are you talking about? Static hello. Weird. The Rust analyzer is going wild right now for some reason. Maybe I need to change the target somehow. Hold on. Change Rust analyzer target to a custom file or custom JSON. Is that possible? Let me go to the settings again and let's check this out. Rust analyzer dot there's check on save. Hold on. I believe it does give. Okay. Check on save. Is that it? No, it's not all of it. Check on save dot target. So I think there's no. Interesting. The property keys must be double quoted. Double quoted, I think. Like this. Oh, my bad. I see. Is that how it should be? Maybe. And known configuration setting. So I guess that doesn't exist. Let's try the other one, I think. Cargo target. Okay, this one does seem to exist, but I wonder if it does accept a custom file name. Okay, dodge this. Okay, restart. And hopefully that would fix it. It does seem like it's using that, right? Maybe. But that didn't fix that. What about this one? I don't know about that. No clue. And by the way, after doing that custom target, do we actually need the panic handler and stuff? Like, sorry, not that. I mean maybe this, well, hold on, where is it? Cargo toml. Maybe we don't need this anymore. What about that? Waiting for file lock. Okay, so cargo check is running in the background right now. Come on. Okay, so that seems to work without it, because I think right now we have that custom target, so that's great. Okay, cool. Alright, anyway, let's go back to what we had, and we're gonna do this. Well, let's just copy this whole thing, really. And let's see. Okay, so here we have an address. As mutable roll pointer, right? And Hinnock, welcome back to the live stream. How's it going, man? And so right now what we do, By the way, I don't have that much experience with NSA for us, but we can try, I guess. So here we actually getting the index of the byte, and we're getting a reference to a byte, and we're iterating through this literal value, this constant right here, and we're enumerating it, of course, to get the index. Then in safe, then we basically offset. This is basically like in C, you would say the pointer plus something, like pointer arithmetic basically, but instead of saying plus, you would say offset, I think. So calculates the offset from a pointer. Count is in units of t. A count of 3 represents a pointer offset of 3 times size of t bytes, pretty much. And this is the safety conditions. If any of the following conditions are violated, the result is undefined behavior. Both the starting and resulting pointer must be either in bounds or 1 byte past the end of the same allocated object. Okay, the computed offset in bytes cannot overflow an I size. And the offset being in bounds cannot rely on wrapping around the address space. That is the infinite precision sum in bytes must fit in a U size. The compounder standard library generally tries to ensure allocations never reach a size where an offset is a concern. For instance, vec and box ensure they never allocate more than I size max bytes. So vec as ptr add vec.len, it's always safe. Okay. Most platforms fundamentally can't even construct such an allocation. For instance, no known 64-bit platform can ever serve a request for 2 to the power of 63 bytes due to page table limitations or splitting the address space. Interesting. We're getting into some virtual space stuff here, virtual address space. However, some 32-bit, I do have some experience with Win32 a bit, but and 16-bit platforms may successfully serve a request for more than I size max bytes with things like physical address extension. As such, memory required directly from allocators. Anyways, that's interesting stuff. So here we got I as I size times 2. But why times 2? Equal to byte. Oh, I think this is basically probably the what is it called? Like when you jump, stride. I think that's the stride. So we jump in from 1 byte, right? Or isn't it? Yeah, because we have two bytes. We're putting 2 bytes. We're putting the first byte is the byte that we got here, and the second byte we're putting 0xb. Yeah. So basically, we'd have something like. Let me try to get this straight. I think you would have h 0xb, right? So this is what would be written into the VGA buffer in this address. So 0xb e, of course, as a byte, right? And 0xb again, and so on, right? So, and yeah. Okay, cool. So that seems to be it, I guess. So now we should run our kernel. And of course, creating a bootloader is its own story. We're not going to be creating a bootloader from scratch. At least not in this stream, maybe in another stream. But creating a bootloader would actually require some assembly knowledge and crazy stuff like that. But anyways, right now we're just going to use a library called Bootloader. And this is in fact created by the ones that are creating Rust, the most popular Rust OS, which is called Redux. So let's see, Bootloader. There you go, an experimental pure Rust x86 bootloader. Of course, this is only for this architecture because, you know, developing for other architectures, it's another story by its own. That works. So if you have a Mac OS, for example, you're probably out of luck because it's probably not x86, I guess. But anyways, that works on both BIOS and UEFI systems running in Rust and some inline assembly, buildable on all platforms without additional build time dependency, just some Rust up components. Interesting. So it uses create, they can create bootable. Add a dependency to the bootloader API, create a new kernel. Interesting. Well, let's start simple by just adding this first of all. And let's see. Okay, so that's how you add a library in Rust. Pretty simple. No CMake that got harmed. And let's wait for it to compile now. Okay, what else? What else? So after adding this, so adding the bootloader's dependency is not enough to actually create a bootable disk image. The problem is that we need to link our kernel with the bootloader after compilation, but Cargo has no support for post-build scripts. Interesting. Makes sense. So to solve this problem, we create a tool named boot image that first compiles the kernel and bootloader and then links them together to create a bootable disk image. To install the tool, go into your home directory. So basically we need to link the bootloader and our kernel because well, the CPU would start executing its stuff on the bootloader, right? But then the bootloader needs to actually launch our own kernel, and how it's gonna do that, it's gonna need to know which is our start function. So we need to link them together. So it knows that we want to start from this function, right? This start function. But yeah, and to do that, it is not possible with vanilla Rust. We don't have post-build script, seems like. So you gotta install this tool that someone more smart from us have made. And let's go. Let's see. So that needs compiling too, of course. It's a binary tool that you could basically use. And of course, when you actually install binaries from crates.io, you have to compile it yourself. Okay, great. So I think we have that boot image right now. It already works, but there's some errors, interestingly. That doesn't seem right. What's up? What is this? What is good? Kernel build fail. I don't even have all this code, bro. Heads. In Linux, you can use the system package manager as your lib package manager. It's nice. It will make building stuff on Windows way harder. Yeah, I would expect honestly to be harder on Linux. On Windows. Interesting. Why there's all these errors? Let me see if they mentioned something about this. I see. Maybe for running boot image and building the bootloader, you need to have the LVM tools preview Rust component installed. You can do so by executing Rust component. Add LVM tools preview. Okay. Component LVM is up to date. Well, it's already added, though it is for that target. How can I add it for my own target? Or does it? What? I see that to recompose. Compose the bootloader, you can and your kernel into a bootable disk image. Oh crap, I just seen errors, bro. How does it work? Boot image tool performs the following steps behind the scenes. It compiles our kernel to an ELF file. Okay, so ELF is basically executable and linkable format. I think it's only used by Linux though. Or is it used by... I don't think it's used by Windows. Or is it? No, I don't think so. Windows have their own thing, right? I think they have that... weird. Anyways, so... this is the format of executables basically, at least on Linux or Unix. Anyways. So, booting in QEMU. But that didn't work. Windows use PE, yeah. There you go. In this next post, we'll explore the VGA. Portable executable. Makes sense. Everything not Windows. Alright. I'm not really a fan of using this magic utility to turn our blob of rust into a bootable image. The parts in raw assembly in the first edition were a bit tedious, but I liked how they gave us a deeper understanding about how the process worked. I hope that this utility won't be sticking around for the post on UEFI booting. They're designed to make the bootloader simple instead of the kernel. For example, the kernel needs to be linked with just said. But yeah, anyone have the same issue as me here, or Some messages are blocked. Do they contain? I do have some filters on for spam, but yeah, told community. Yeah. No one does. Oh, well, here's a big error, I guess. I get the following error. No, that's another issue. Cargo boot image dash Z, which is weird. Oh. Version used. Try the latest version to give you the same errors. Are used in an entirely different way. Okay. Okay. Hold on a second. So I think the bootloader have. Well, actually, we can look up the bootloader documentation and try to figure it out on ourselves. But honestly, right now we're still noobs. I don't want to go that rabbit hole right now. I don't feel that adventurous. So, okay, it seems to. No, actually, we should do this cargo boot image like this. Okay, I think the magic is happening. So apparently, you need to use, right for now at least, 0.9 bootloader. Because the last version have changed from the guide. Okay, hold on a second. We have created our first boot image for our OS. Yeah, boys, we're gonna ditch Windows right now. Create boot image for Kodochaku OS at. Okay, where's my OS? I think this is it, or is it? Where the fuck is it? Okay, it's here. There you go. It's not an ISO though. I'm used to ISOs. It's a bin file. Flash it on a USB and run native. I don't want to ruin my computer. Don't want to burn it. Don't trust my code. So anyways, so there you go. We got our binary. It's 62 kilobytes. That's our OS. The real question right now is how to run it. The real question right now is how to run it. So here's, by the way, how to actually run it on a real machine. So you would write it using a USB stick and boot it on a real machine, but be careful to choose the correct device name because everything on that device is overwritten. You would lose all of your data on that disk. So, but this only would work on Linux using DD. Though on Windows there is Rufus. I think it would work the same way. At least that's what I use. But there you go. You can use this. But I would rather not install my own OS in my own machine. That would probably not end up great. So where SDX is the device name for USB stick. I should write it. I'm pretty much used to user mode, not using to kernel mode in limited power. Just let me on my own virtual memory, please. I don't want physical memory. After writing the image to the USB stick, you can run it on real hardware by booting from it. You probably need to use a special boot menu or change the boot order in your BIOS configuration to boot from the USB stick. Note that it currently doesn't work for UEFI machines, since the bootloader crate has no UEFI support yet. But it may at this point, though, because this guide is a bit old, maybe from 2017, I'm not sure. But we have to actually check out the new guide of Bootloader. To make it easier to run on kernel and QEMU, we can set runner. Okay, so how to run it on QEMU? First of all, I need to actually install QEMU though. I don't have it on my system. I always wanted to try QEMU. I only tried VirtualBox. QEMU and VirtualBox, at least from my understanding, it seems like kind of like comparing Windows to Linux. So like VirtualBox is easier to use, but QEMU is possibly more performant and more flexible if you know what you're doing, if you're a power user, I think, at least. But if you guys know any more crazier differences, please let me know. But this is the first time I'm going to be using QEMU 2, pretty much. Okay, cool. Windows. 64-bit binary. What the heck? 2023. I think this is the one, right? Yeah, I think so. exe. Okay. Let's go. By the way, I still don't know how to actually verify executables using using these hashes in Windows. I know how to do that in Linux, but in Windows I have no clue. I tried, but I failed. Does anyone know? Well, I thought it's a front end for Linux kernel virtualization feature. A generic and open source machine emulator and virtualizer. You hash the executable and compare. But how do you hash the executable in Windows? NXN with near native performance. User mode emulation. Full system emulation and virtualization. That's some pretty cool stuff. But let's wait for it to download right now. And otherwise, we're gonna need to do it this way. Execute the following command: QEMU system x86-64-drive format raw, because that binary is a raw file. Oh my god, this reminds me of the day when I did an update for my BIOS using Windows updates, Windows optional updates, and it broke my BIOS. And I couldn't even find someone to repair it in my city. No one have the device to do that, or at least not the experience to do that. Yeah, they probably do have the device, but they don't know how to do it. So I had to go to another city in my country to actually... I could have done it myself, but I don't have the tools. And I've never done welding ever. But I would like to if I had the tools, but yeah. Git dash file hash path my file exe dash algorithm. Nice. Okay, let's try that. Why not? I actually searched on Google how to do that, but I didn't find anything. But well, anyways, where's the hash again? I gotta go again. Okay, hold on. Windows 64-bit and SHA. Okay, so this is the SHA or the hash. Cool. Okay, so you essentially grab a CMD here. Okay, though maybe I would need PowerShell. Let me try it here though. Okay, no, I can't do it here. I need PowerShell. Yeah. Okay, let's cd into here and git dash file hash, and it's called QEMU. Okay, cool. And dash algorithm SHA-200. And for the people who doesn't know, this is basically a way to verify, to make sure that you got the executable, like the exact executable that you're supposed to download without any tampering or something like that, right? But this seems like a different hash. Did I get the wrong executable? The QEMU-W64 setup. What the heck? Oh, Shaffer. I see. My bad. Alright, but how do I compare those? Do I need to use Python? Or... And I don't think I see the whole hash, or do I? Is there an easy way to actually compare the hash directly? Any idea? But maybe we could say Python. I'm not aware of a command in Windows to do this. Maybe we could... Probably should make this into a string. Get file hash as a utility, probably. Oh. Get file hash dash h. No. Dash help. What the heck, Windows? Okay. Dash pass. Count parameters. I don't see anything there. But anyway, I think it looks the same pretty much, honestly. So it's fine. There you go, A54FD at the end. I don't see the whole thing for some reason, but whatever. Anyway, that's how you do it, I guess. Alright, anyways, let's actually run the executable. Run the setup. Okay, let's go. Okay, I ran the executable, yes. English, okay, next, agree, install, and let's wait for it to install. And meanwhile, we could check out, okay, so this is how you use Bootloader library here. You would actually add a dependency on the Bootloader API crate in your kernel toml, so you would add something else, right, some other library. We already have that. Define an entry point function with the signature this way. Okay, so you would use a kernel main function. The boot info argument provides information about available memory. QEMU has been installed. Finish. Okay, does it automatically add it to the path? I would guess so. Oh, maybe x86. Oh, there. Not this actually. This is min-gy. Okay, how do you do it? Where is it? QEMU, that's system. Maybe I have to add it myself to the path. Oh, weird. Maybe I have to run it from here. What? How do I run this? Probably need to add it yourself. Okay, gotcha. So let's go to where it got installed. Where it got installed? Good question. Let's try to run the setup again and see where it got installed. Come on, come on. Bruh. Okay. Next. Okay, so here. Makes sense. Alright, so this is where it got installed, and it should have the binaries here maybe. Okay, cool. There you go. Cool. So let's add this to the environment variables. Path. QEMU. Okay. And now we should be able, after restarting our terminal, we should be able to actually call it. Oops. Oh yeah, there you go. Cool. So dash system. Okay, cool. I don't think we can run it right now through VS Code until we actually restart it. So let's restart VS Code to refresh the environment variables. And now we should probably be able to do that. I hate that Windows doesn't have executable folders. It's so annoying. What do you mean by executable folder? QEMU dash system dash, and here you basically tell it, oh my god, what happened there? You basically tell it the architecture that you have. So QEMU dash system dash x86-64. And what I need here, I need this whole thing. Let's just copy it honestly. Or, you know what? Let's just type it. Dash drive usr/bin like a folder follow. Oh yeah, that's true. That's very, like, it should have a package manager. I mean, it does have a package manager, but that's nowhere near a Linux package manager. Anyways, dash drive format equal raw, comma file equal to, and here you basically give it the path to your file. Okay, format equal to raw because it's binary. And here I think the path, or is it? Actually, that's the format, my bad. Okay, format equal to raw, comma file is equal to, and let me copy the relative path to this guy. I don't know if it's actually would be good, honestly. Let me make a text file real quick, because they have this stupid backslashes. Windows, ladies and gentlemen. And let's go. Okay. There you go, your Hello World operating system. It works. Could not load a pixbuff from icon theme. This may indicate that pixbuff loaders or the MIME database could not be found. Hello World. Let's go. We're of course just using the BIOS, I think, here to print stuff. But yeah. Alright, so I think let's go to the next step. Or maybe we could try to get the bootloader working, possibly. But hold on, let me first of all make this into a repo. So cargo tunnel, raster change settings. Okay, let's actually save all changes. And hello world. Commit. Guys, this is just hello world. I don't know what we can. The moment when you realize you have just made the hello world. Yeah, I remember how that started. It didn't go that well. The hello world was all fun, you know, but later on, and I want to run on my computer. I'm gonna make this into a repo, and then you could easily just compile it and run it however you want. It would be fun to get some graphics going. Oh my, that's probably very, very far. In fact, I don't think this guide gives us that. I don't think this guide would give us graphics. At least not yet. It doesn't have graphics just yet. In fact, it doesn't have a lot of things yet, but it does have the basics of a kernel. It would be fun to get some. Yeah. Okay. So what I wanted now. Yeah, I need to publish this guy. Message. Well. Okay. Write the GPU driver. Easy. Maybe we could use LVM. You know, LVM. What is it called? LVM lava pipe. Yeah, LVM lava pipe. For that, for software-based GPU driver. You know, Vulkan driver. But that uses the CPU. But anyways, so okay, so how can I publish this? Let's go publish to public repository. Let's open on GitHub. And actually before that, let me just put how would you actually do this? Oh yeah, I remember the guy told us something interesting to make this automatic. Really, hold on, where is it? Thank God we're using Rust. Yeah, here. So to make it easy to run our kernel in QEMU, you can set the runner configuration key for cargo. So cargo config choml, we would add this target OS equal none. Okay, and there you go. So I guess you would add boot image runner, and is that it? Applies to all target configuration file OS field is set to none. This include our, makes sense. The runner key specifies the command that should be invoked for cargo run. Ooh. The command is run after a successful build with executable path passes first cargo document. Designed to be used as the runner executable, it links to given executable in the project. But how does it know it's QEMU? How does it know that? Oh, it actually uses boot image tool that we have installed, I think. Now we can use cargo, yeah. Okay. I think it uses the boot image tool that we used, and then maybe that basically calls into QEMU. Probably. Now if we do cargo R, there you go. It's that simple. No crazy stuff. You know, just clone the repo, cargo R, boom. That's it. You got the OS run. As long as you have, what is it called? QEMU on. But anyways, so let's also add that README actually. While we're at it, readme.md. Simple OS being made in live stream. Okay. Or let's say my first OS being made in a live stream from scratch, following this guide. Oops. Okay, let's link. Oh, let's just link to this. I think, well, hold on, let me copy this whole thing. There you go. Or, I mean, we could just say this too. I think. There you go. Following this guide. Let's go. I'm just gonna put the stream's URL for now. It's not from scratch. You're using the CPU instruction sheet. I mean, it depends actually on how, like, what you're like, which level is from scratch, because from scratch is it's actually pretty broad. But yeah, let's just remove it honestly to avoid conflict. But yeah, anyways. Alright, so that's basically it, I think. And let's just add an MIT license, maybe. Just joking, keep it down. License.md. Let me just copy the license from one of my repos real quick, because I'm not a lawyer. Makes me feel bad. Which is the latest one? Okay. Oops, not my scripting language. Where's license? There you go. Let's copy this bad boy and let's paste it here. And we should be good to go. Okay, so let's just, is there anything else? I don't think so. Let's do this. Get whistles. Is whistles how? What the heck? I don't know how to spell whistles. I forgot how to spell whistles. Or is this correct? Hold on. Okay, cool. Alright, so commit and let's sync the changes, okay? And there you go. one last step just to make sure that this works perfectly. I'm gonna add hold on, where's my repos? Okay, so I'm gonna add some GitHub workflow action to make sure it works properly for other people, because it actually would it yeah, let's just try anyways. Let's configure. English is annoying. What do I pronounce it? True. So cargo build verbose, cargo build. Okay, let's see. Would this be able to compile our OS? Good question. Okay. So let's see if this works. Otherwise, I'm gonna be missing something. And by the way, hats, right now you can actually go to the repo and try it on your own if you want to. Oops. There you go. I mean, oh crap. All checks have failed. Interesting. Why? Does not exist. A cargo lock does not enable to build with the standard library. Huh. Try Rust up component, add Rust src. Rust build take ages. Oh, right. Interesting. So it didn't actually work here. Tool chains nightly. Why it's using this tool chain though? It's not using the tool chain I think I've told it to, or is it? I don't know how to fix this. Rust git workflow. Oh crap. Let's go. Oh my, no way. Well, let's copy something smaller. Enable to build a standard library. Okay, enable to add a component. Get the following error. No clue. Anyway, let's not waste more time on this for now. But if anyone knows, please let me know how to fix this. But for now, our stuff doesn't work in Git workflow. But anyways, so let's go to the next step, I think. I should probably read through this after the stream. But we'll see. Unless if I get stuck here. VGA text mode is a simple way to print text to screen. In this post, we create an interface that makes its usage safe and simple. By encapsulating all in safety in a separate module, we also implement support for Rust formatting macros. Okay. So the VGA text buffer. To print a character to the screen in VGA text mode, one has to write it to the text buffer of the VGA hardware. The VGA text buffer is a two-dimensional array with typically 25 rows and 80 columns, which is directly rendered to the screen. Each array entry describes a single screen character, through the following format. So 0 to B is ASCII code point, 8 to 11 bits are foreground color, and 12 to 14 background color, and the other is blink. Huh? Each array entry describes a single screen character through. Okay, so it's 16 bits, right? Yeah, 16 bits. So the first 8 bits are for the ASCII code. The other bits are for the foreground color, background color, and blink. Okay. To be more specific, it isn't exactly ASCII, but our character set named code page 437 with some additional characters, slight modifications for simplicity. We'll proceed to call it an ASCII character in this post. Okay, so this is it. Is the character set of the original IBM PC, personal computer. Okay, cool. So this is all the characters that you could use, pretty much. Okay, cool. So the second byte defines how the character is displayed. The first 4 bytes define the foreground color, the next 3 bits in the background color, and the last bit whether the character should blink. The following colors are available. Cool. Via memory mapped IO to the address 0xb8000. So this is the VGA text buffer. Okay. So this thing right here is VGA text buffer address. I think this is how we do constants, right? Come on. Okay. And I believe maybe use size. Okay. And that should work as before, pretty much. Just making sure. I'm paranoid. Anyways, note that memory mapped hardware might not support all normal. Shama Sinha, welcome to the live stream. How's it going? So note that memory mapped hardware might not support all normal RAM operations. For example, device can only support bitewise reads and return junk where U64 is read. Fortunately, the text buffer supports normal reads and writes, so don't have to treat it in a special way. What? Rust module. Now that we know how the VGA buffer works, we can create a Rust module to handle printing. Okay. For the content of this module, create a new src VGA buffer RS file. Okay, let's go ahead and do this. Let's make, where is it? By the way, what we have changed again here? Nothing fancy. So right now, let's just make a new module, new Rust module. And we're gonna call this, I guess, VGA buffer, right? Is that it? Doesn't really matter, but okay. Okay, but where is it? It didn't get created. Huh. Weird. Anyway, let's create it ourselves. VGA buffer.rs. There you go. And we're gonna include this module. So mod VGA buffer. And now first we represent the different colors using an enum. Let's just copy this. Okay, so we just have an enum color with all of these enums from black to white, pretty much. And it's repr U8, meaning this should be interpreted as U8. And allow did code, derive, debug, clone, copy, partial AQ, and AQ. Okay, cool. So we use C like enum. Cool. Oh, hold on. Each enum variant stores U8. Actually, 4 bits would be sufficient, but Rust doesn't have a U4 type. Zig does. Zig, you can actually do a U4 enum. Normally, the compiler would issue a warning for each unused variant by using... Though, this is not really used efficiently unless if you, at least in Zig, unless if you use the packed struct, which is really what it is meant for, is for serializing data. Anyways, normally the compiler would issue a warning for each variant. Cool, by deriving the copy semantics, okay. Top of U4. Okay. To represent the full color code. But why it's UH? Oh, because it's just the color code, not the whole thing, right? Okay. And it's transparent. Why? So to ensure that the color code has the same data layout as a U8, we use the wrapper transparent attribute. Okay. Text buffer, and we also have this ample color code, which basically takes a foreground color and the background color, and it do some bit shifting, right, to merge them together into the layout, to the bit layout that he described before, basically. So that makes a little sense. So we basically take the foreground in the lowest bits, right, and shift, and basically after 4 bits we use the background color then. Or is it? Hold on. What? Why? Shouldn't it be 8 bits? Oh, my bad. It is U8. Yeah, because we cannot use U4. I forgot. Yeah, makes sense. Great. Okay. So that makes all sense. We derive the copy and debug traits to ensure it has the exact same data layout as the wrapper transparent attribute. We can add structure to represent screen character with text buffer. So here we have a screen char color code. Okay, so U8 and U8. Buffer height, buffer width, buffer. Of course, we do not have the heap because we do not have an OS. We're creating the OS. And even the stack, I'm not sure if we have actually initialized it at this point. We probably did, maybe? I don't know. Maybe that's the job of the bootloader, I'm not sure. But anyways, so here we have an ASCII character, nothing fancy, just simple stuff right now. We just have an array, well, a 2D array as a buffer with these. We need to wrapper C. Yeah, you need to make sure. Well, where's wrapper C? Hold on. Okay, it's in screen char. Because we gotta make sure that the layout matches what like C code would, for example, expect. Because otherwise, the compiler is free to actually reorder these fields as it wants for optimization purposes and so on. But yeah, we just use wrapper C to make sure that doesn't F up. And here wrapper transparent, same thing, though I'm not entirely sure there's a difference between transparent and wrapper C. But anyways. To ensure that it has the same memory layout as the single field. Oh, actually, I think wrapper transparent, what it actually does maybe is, you know, like in C, to do inheritance, I think you kind of like, basically you can use the first field, you can reinterpret the whole struct as the first field and use that. I think that's what it allows here, maybe, but I'm not sure. We now create a writer type, column position, color code, and the buffer, and static mute buffer. Okay. And the writer always writes to the last line and shift lines up when a line is full or on a new line. The column position field keeps track of the current position in the last row. The current foreground and background colors are specified by color code, and the reference to the VGA buffer is stored in buffer. Note that we need an explicit lifetime here. How long the reference is found. Static lifetime specified that the reference is valid for the whole program runtime, which is true for the VGA text buffer. Makes sense. The program in this case is our OS, is our operating system. So makes sense. So basically this writer struct keeps track of the position of the cursor, kinda. So the column and position, the buffer address, and or the reference of the buffer, and the color code that we are currently using. Okay, now we can use the writer to modify the buffer's character. First, we create a method to write a single ASCII byte. And if the byte is the new line byte, the writer does not print anything. Instead, it calls a new line method, which we'll implement later. Other bytes get printed to the screen in the second match case. Okay. Alright. Let's see what we got here. What's happening? So we got a write byte function on the writer, and we take a byte. Okay. We take a byte. Okay, match byte. If it's a new line, then we use the self.newLine function here for some reason. And otherwise, if it's any other byte, then we check if the column position is greater than or equal to the buffer width. If that's the case, then we jump a new line. And yeah, we keep on going. Let row is equal to buffer height minus 1. Okay. So, and call is self.column position. Then the color code is self.color code. Self.buffer.chars. Buffer. Yeah, I see. .chars row column equal to screen char ASCII character is the byte. And the color code. Okay. Self.column position plus equal 1. Or instead of doing this, I mean, we could just also just say this, honestly. Isn't it? Although it's not technically ASCII character, but it's kinda. Anyways, and after that we advance the column position, which makes all sense. Okay, cool. Righty, now makes sense. Okay, and what we gotta do in the new line then? When printing a byte, the right checks its current line is full. In that case, the new line calls is to wrap the line. You can convert them to bytes and print them one by one. But what about the new line? To print whole strings, you can convert them to bytes and print them one by one. So it gets the bytes of the string, and then we match on the byte. If it's a printable ASCII byte or new line, then we write the byte. Otherwise, not part of printable ASCII range. So we write this byte, which I would guess maybe symbolize. Let's support additional byte for strings. Are UTF-8 by default, so they might contain bytes that are not supported by the VGA text buffer. We use a mesh to differentiate printable ASCII characters or bytes, a new line, or anything between a space character and a character like that. So to differentiate printable ASCII bytes, a new line or anything in between a space character and that character, right? And then printable bytes. For printable bytes, we print we print this character which has the hex code 0xFE on the VGA hardware. Okay, try it out. To write some characters to the screen, you can create a temporary function. Alright. Let's copy, paste. Nothing fancy until now. And okay, no need for these comments now, not part of printable ASCII range. Write the byte. And I think this is basically for a square, but anyways. I think we could probably say B okay, where is it? A new line or anything between a space and a space. I think we could probably do something like this, maybe. Right? I think so. I mean, we can check the ASCII table. We can check the ASCII table. But I don't know if I can actually trust that. It may depend on the system. When are those ASCII? But I don't think that's the case. Maybe. I'm not sure. Anyways, let's try to find one. Let's look for... Okay. So you have a space. There you go. Which is hex 20. Is that right? Yeah, 0x20 and 7e. 7e, which is the last tilde, right? Where's tilde? Bruh. There you go. 7e, yeah, pretty much. So I think we could probably just do it like this instead of using the hex code. And what 0xFE is. 0xfe. Or hold on a second, if we go back to this code page right here, is there an interrogation mark? Because that's, I think, what's usually gets printed. Or isn't it? There's the 02, yeah, 024. I think this is what he's trying to. Either way, let's just leave that as it is right now. Anyways, and now what? Try it out. Try some character to the screen. You can create a temporary function. So print something like mutable writer. So you create your writer. You start by the column position 0, color code new, color yellow, black, and buffer and safe. Oh crap. Mutable reference. Okay, so first of all, we actually take 0xb8000, which I think is the VGA buffer. Yeah, makes sense. So it's honestly, instead of doing it this way, we can just make a new function, really. So let's make a new function here. Okay, and let's just return this. There you are. Actually, no need for return, yeah. There you go. And here are the color codes. Okay. Yellow and black. So new, this one is the foreground and the other one is the background. So color black, yellow. Okay, cool. What else? Write byte. So now I could use that writer to write bytes or write a string, which is pretty cool stuff. The syntax for this might seem a bit strange. And honestly, by the way, let me grab this VGA text buffer address. Oops. Let me do it maybe, I don't know, here. And honestly, I don't think there's a need for VGA text. Just say VGA buffer address, memory mapped address. But anyways, VGA buffer address, and we're just gonna use that as a mutable buffer. Cool. So now, but hold on, we haven't implemented the new line yet. Interesting. So now, instead of doing this, but hold on, what about the 0xb? Oh yeah, I see now. Now I understand what the 0xb for. It's for the color coding, I think. Yeah, pretty much, because it's 16, so 2 bytes, yeah. Makes total sense now. Okay, so what did I call it? Impl writer. I just call it writer, seems like. Okay. VGA buffer writer new. And what's up? I think I need to make it pub. Yeah. Pub fnu. Now we created the VGA buffer writer. Now what we had before. Okay, I think, well, write string, yeah. And here we could just say hello world. And cannot mutate. Oh yeah, should be mutable, I guess. And there you go. Let's try this out. And it works. Good. What if I write even more hello worlds? Does it still work? Great. What if I write a lot of hello worlds? Let's say 100 times for each. Closure is expected. Yeah, okay. I don't care. Oh, it doesn't actually. Yeah, I mean we haven't implemented new line yet, so that makes sense. It creates a new write that points to VGA buffer. The syntax this might be strange. First we cast the integer, this, yeah, as a mutable row pointer. Makes sense. Then we convert to a mutable reference by dereferencing it through that. And immediately borrowing it again. What? Oh, okay. This converter requires an unsafe block since the compiler can get treated that the row pointer is valid. Then it writes the byte BH to it. The B prefix creates a byte literal which represents an ASCII character to call print something. Why this is like this? Huh? Oh, because there's those characters, I see. Makes sense. Property individual bytes multibyte are never valid ASCII. Makes sense. So this actually translates to 2 bytes, right? Because it's UTF-8. Now volatile. I know this a bit. It's used for memory mapped addresses because like the compiler is actually free to order your variable stuff and basically your whole program, all the instructions, as long as they can guarantee that that ordering wouldn't affect the outcome of the program, like like it should basically behave the same way, but it can optimize it by reordering instructions and statements, or even removing them or whichever. But this problem is for memory mapped addresses, like the one of the VGA buffer here, is that it could potentially be that like basically the compiler doesn't know that that VGA buffer can change without you actually changing it, right? And what could happen is that it could optimize something out which would corrupt everything, right? Because the compiler is basically assuming that the value wouldn't change, the value in the pointer wouldn't change as long as your program haven't changed it. But that is not true. I mean, it could technically change because when that's just memory mapped address, right? It's not an address in your own virtual memory as you would have in a normal program. But yeah, like you don't have control over it, so you'd better use volatile for that. Though I never use volatile in Rust, I only used it in C. We need to specify these writes to sell the compatible write side effects and should not be optimized that way. There you go. Writes to VGA buffer use volatile. This is how packages are called in Rust. Word provides a volatile wrapper type with read and write method. These methods internally use the read volatile and write volatile functions. The core library does guarantee that the reads and writes are not optimized away. Okay, so we just cargo add volatile. Okay. Okay, cool. So we added volatile. Are not compatible with this post. Interesting. Why? All right. Let's make sure to do that. For now, we're gonna live in the past when it comes to versions. We update our buffer type as follows. So instead of screen char, we're gonna go with volatile screen char. Where is it? There you go. And cannot find volatile. Let's import it. And there you go. Can wrap elements anytime. So yeah, right now we have to use the write function. So let's go ahead and do this. I think write. Okay, cool. And I guess maybe that's how we do it. Oops, gotta go R. Making sure everything still works correctly. Great. Now it does work the same, but it could potentially not work properly without that volatile there. We're now using the right method. Now we can guarantee that the compiler never optimize away this right. Formatting macros. Rust formatting macros too. The way we can easily print different types like integers or float to support them, we need to implement the core FMT write trait. The only required method this trait is write_, which looks quite similar to our write_string method, just with an FMT result return type. Interesting. OK is just an OK result containing the unit type. Now we can use Rust built-in write and write_line formatting macros. Okay. So use core FMT write writer. Oh, I can use this macros. Okay, that's cool. And now we can actually do formatting stuff. Interesting. Interesting. Okay, let's implement this trait. For the writer here, VGA writer. Let's maybe do it here. What are you doing right now? Right now, just implementing formatting macros for the VGA buffer writer, so we can be able to use the Rust formatting like this, basically. Yeah, write string s FMT result. Okay, cool. Now we can, I guess, basically instead of this, I think we could say write, and then what should we pass here? Writer, right? Don't use this macro. Writer, yeah. And we unwrap because it returns a result. Okay, and then here I think format. Yeah, the format and then the arguments. Cool. Hello world. But what's up? Cannot write. Yeah, I think I need to import the trait. So what is the trait called that I need to import? Where is it? It doesn't mention it here. Let me just try to run this and it would tell me. There you go. I think this is the one. Because to use that write macro, I think you have to import this trait. And there you go. Good. Now what if I said I here and do this? Interesting. Okay, cool. Let's just remove this whole thing, honestly. Just keep only the numbers with a space after them. And yeah, we have Rust formatting right now. Great. Though I really wonder how it actually really works. Not gonna lie. Because like, what? I mean, I thought this would need like the heap to allocate stuff. Or, I mean, it probably just, yeah, it's a macro, so it would probably compile some stuff to just write directly. Yeah. Okay, that's cool. I don't think you can do this in other languages. Anyways, right now we just ignore new lines and characters that don't fit into the line anymore. Instead, we want to move every character one line up. The top line gets deleted and start at the beginning of the last line again. To do this, we add an implementation for the new line method of writer. Huh? To do this, well, show me the code. So this is the implementation of the new line function. Okay. To do. Let's remove this to do. I'm probably gonna make this into some functional spaghetti. This is not my style. No method named clear row. Yeah, we need the clear row function. But I'm still a student for now. Clear row. Okay, cool. So for row in buffer from 1 to buffer height and column in from 0 to buffer width. I think in Zig it would be simpler, I don't know, but the Rust macros in my experience makes everything much harder. I'm not sure, I would honestly also expect Zig to be easier. In fact, like someone asked me before about like making an operating system, and I actually recommended Zig instead of Rust because I know in safe Rust can become varying wildly, even for me. But honestly, the experience so far with Rust, it wasn't as bad. I'm not sure about other languages. We should try other languages too to see how it. But like the thing about Zig is that there's not a lot of resources out there, so you may get stuck in something that's still being. I don't know. I don't know. We just have to try it pretty much, or someone have tried it and tell us your experience. Omar Al Khotri, welcome to the live stream. How is it going, bro? Long time. Let character is equal to self.buffer.chars row call.read. So here we perform a volatile read of the contained value in that character. Okay. What we do with that? Yeah, I usually follow C tutorials and do it in Zig. It's painful though. Yeah, but the thing is, you need more than C tutorial. I'm good, Omar. Thank you for asking. Usually follow C. The thing is about C tutorials, it wouldn't tell you about the tool chain stuff, right? The tools on how to do all that crazy linking stuff and so on, you know. So in Zig, it would probably be a little bit different than in C. So as you see right here, I would have not been able to follow with the C tutorial and actually make an operating system in Rust. It's just so much different, and in fact, I think it's better. It's easier, especially with the Bootloader library and such. You don't have to actually even touch assembly for now. But yeah. Anyway, so here we're basically reading that, and then we're going to. Does the row start from 0 or like from the top or the bottom? But basically here we want to move every character one line up. Top line gets deleted. And start at the beginning of the last line again. So why we delete the top line and then... Interesting. We iterate over the screen characters and move each character one row up. Note that upper bound range notation is exclusive. We also omit the 0th row. The first range stars 1 because it's the row that is shifted off screen. To finish the new line code, we add the clear row method. So we created the blank character right here with the current color code, and we basically go through all the columns, right? And we write blank. Okay. Well, let's go. And let's see, buffer height -1. Well, let's see how this actually works, because I have no idea what he's talking. I mean, I understand, but how? Okay, so it actually does right now do that. Nice. It actually goes to the new line right now. Pretty cool. So, okay, but how does that work? Oh, I think because we're probably writing from the bottom up. Is that the case? What? I'm confused. So the row, we go from 1 to buffer height. Anyways, I guess we'll find out later. A global interface. To provide a global writer that can be used as an interface. So carrying a writer instantly, we try to create a static writer. Okay. So we create one writer for everyone. Okay, cool. So static that cannot call non-const a function in statics. Interesting. There you go. I think we need to use lazy static. Yeah, there you go. That statics are initialized at compile time in contrast to normal variables that are initialized at runtime. Interesting. The issue with color code noob would be solved by using const functions, but the fundamental problem here is that Rust's const evaluator is not able to convert raw pointers to references at compile time. Maybe it will work someday, but until then we have to find another solution. Okay. So lazy statics. The one-time initialization of static with non-const functions is a common problem in Rust. Fortunately, there already exists a good solution. A crate named lazy static. This crate provides a lazy static macro that defines the lazily initialized static. Instead of computing its value at compile time, static lazily initializes itself when accessed for the first time. Thus, the initialization happens at runtime. So arbitrarily complex initialization code is possible. Okay, cool. Lazy static spin no std. Let's just copy this. I'm gonna use the same version as the guide for now to not have any problems. In fact, it is the last version, it seems like here, maybe? Or is it? It does seem like there's 1.4 maybe. But anyways, let's compile this crate real quick. Oh, well, we have to fix that first. So now we need the spin no std feature since we don't link the standard library. Okay, interesting. So I guess instead of a mutex and interrupts and stuff like that, I think we're basically just spinning infinitely, like using a loop to wait, like a while, a simple loop, right? Which is not great, not the best, because you're gonna be constantly, you know, working out the CPU, giving it a workout while you just want to wait. But like to do this optimally, you have, I think, to work with some CPU interrupts to kind of like let it sleep or something like that, and it would wake you up, I guess. I don't know exactly, but anyways. So let's actually use this lazy static as they said. Though, hold on, where is the code again? VGA buffer. So this is what we have right now, pub static. Let me just copy it besides it and just see what is the difference. So here we have pub static writer. Here though we have a ref writer. Okay. Equal to writer, column position, color code. Well, here actually, can we just say color writer new, pretty much? Because we made that function. Cannot find macro lazy. Yeah, let's actually add it. There you. Oh, what? The name writer is defined multiple times. Oh, well, makes sense. But basically here we also have writer new. So that's the difference. Instead of pub static writer like this, that can't happen because this would run on compile time, which is not possible because we cannot dereference a pointer at runtime, well, at compile time. We use lazy static instead to initialize it the first time, you know, you access it, kind of like a singleton to some degree. There you go, writer new, and yeah, it's pretty useless since it is immutable. This means that we can't write anything to it, as all the write method take mute self. One possible solution would be to use a mutable static, but then every read and write to it would be unsafe, since you could easily introduce data races and other bad things. Using static mute is highly discouraged. There were even proposals to remove it. But what are the alternatives? We could try to use an immutable static with a cell type like refcell. Use an immutable static with a cell type like refcell. Or even in safe cell, basically interior mutability, but these types aren't sync with good reason, so we can't use them in statics. Sync basically means that, well, hold on, let me try to remember. So there is sync and send. Send is basically the ability to send data between threads, and sync is the ability to, yeah, change data between threads, mutate data between threads, I think, if I remember. Anyways, so like a mutex, I think, is sync and send. Actually, not send, maybe. What? I don't remember. Anyways, so we can't use them in statics. Okay. Spin locks to synchronized interior mutability. Users standard library can use mutex. There you go. It provides mutual exclusion by blocking threads when the resource is already locked. So as you can see, the operating system usually, like you would use mutex, which the implementation will go ahead and do some function calls like syscalls, system calls to the operating system, you know, to schedule your your sleeping period for that thread, right, and stuff like that. But yeah, like to basically do it optimally. But here, since we don't have an operating system, we're actually creating the operating system. We're just gonna use a spin lock, which, as I said, it would just let me just read this. Does not have any blocking support. Hold on. By blocking. But our basic kernel does not have any blocking support or even a concept of threads, so we can't use it either. However, there's a really basic kind of mutex in computer science that requires no operating system features, the spin lock. So the blocking thread, simply try to lock it again and again in time loop. Does burning CPU, this is exactly what I said before. Burning CPU time until the mutex is free again, which is not great, but it works. To use the spin mutex, we can add the spin craze, depends. Though I think after that, they would have like a guide for implementing crazy stuff like this. But anyways, cargo add spin. Okay. To add safe interior mutability or static writer. Spin mutex. So we use the spin mutex instead of the standard library mutex. This is a global, that's why we need this stuff. So mutex new, right? Mutex new writer new, is it? I think so. Found struct, oh yeah, mutex writer here, and there you go. Can't I just remove this type though, by any chance? No. Okay. Because it's a static, seems like. Now we can delete the print something function, print directly from our start function. Interesting. So now instead of every time having to create a new VGA buffer for no reason, like VGA buffer writer, sorry, we could just say, I think, VGA buffer writer. Just like that. And I think we have to lock it, right? Yeah, I think so. Probably have to lock it. There you go. Okay, makes sense. I mean, it's a mutex. And there you go. Now, I do have an interesting, what is it called? An interesting analogy for locking mutexes. Like yesterday I was on the gym, right? And I was using one machine because I was waiting on another machine that is in front of me used by someone else, right? So it's kind of like every machine in the gym, you know, it's all shared between all of us, right? So it's kind of like I've seen it as every machine is under a mutex. And whenever you start training a machine, you lock the mutex so no one can train otherwise on that machine until you're done, and then you unlock the mutex. But what happened to me at the gym is that I realized that I'm in a deadlock. Basically, so I was waiting for another guy to finish with one machine that I wanted to train on, right? And meanwhile, I just wanted to train on the machine next to it. So I don't waste time, you know. So we gotta get some gains in the gym, right? All the time. So the thing is, I was waiting for him to finish, but he was also waiting for me to finish at some point. So when he finished with this train on that machine, he probably wanted to go into the machine that I'm waiting in. So I'm waiting for him, and he's waiting for me to finish with the machine, and we end up in a deadlock. Right? So we would have waited indefinitely, right? So what I've done to test my theory, I basically gone to an alternative machine after I realized. And then he basically have gone to the machine that I was in, and then I took that machine that I was waiting for. So every time you have a problem, you could probably fix it with one indirection. But yeah, that was pretty fun. That was pretty cool. Anyways, so let's see if this works. Cargo R. And let's go. And yeah, it works just like the same now, but right now we could just use that lazy static instead of creating a new writer every time. There you go. We just have to make sure to lock it. Okay, cool. Cool. We need to import fmg write tray in order to be able to use its function. Safety. Note that we only have a single unsafe block in our code, which is need to create a buffer reference pointer to 0xb8000. Afterwards, all operations are safe. Rust uses bound checking for array accesses by default, so we can't accidentally write outside the buffer. Thus, we encoded the required conditions in the type system and are able to provide the safe interface to the outside. Makes sense. So basically what it's saying is that we have one unsafe block, which is this, right? So this is the unsafe operation that we're doing in our whole thing, right? Which is we're taking this random arbitrary, I mean, at least to the compiler it seems random, arbitrary address, right? And we're basically dereferencing it as a mutable buffer, right? So the compiler, of course, cannot check if that's a valid reference, if that's a valid pointer or not. And we actually cast it as mutable buffer, and basically buffer is actually, as you can see here, an array of screen chars, buffer width and buffer height. And though the volatile doesn't matter, I think it would be the same size. Yeah, there you go. The side of the struct the same as the side of the contained type. So the memory layout would be the same as, so volatile screen char would be the same as screen char, just, you know, that the compiler wouldn't optimize it right away because it's volatile. But yeah, you can see here that we basically used unsafe once, but we didn't use it anymore since we have basically made that reference as a array, a bounded array of buffer width and buffer height, and then the Rust compiler could actually check to make sure that we're accessing it correctly. So that's the nice thing about Rust. You can do your unsafe operation only in one, or like places that are well defined, and then later on you would just use a safe interface. So if anything goes wrong, you should probably look into your unsafe place. But anyways, so does we encoded the required? Okay, cool. Print line macro. Now that we have a global writer, we can add a print line macro that can be used from. Okay, nice. Code bit. Rust macro syntax is a bit strange. I've never used macros, Rust macros before. I just never needed them. I either, like, all the macros I've used so far is either made by someone clever than me in the library, or from the standard library pretty much, but I never needed to make my own macro, at least not yet. Still, we'll look at the source of the print line macro in the standard library. And honestly, macros are quite complicated in Rust, although way more flexible, way better than, let's say, C macros, which is just substitution. But in Rust, you know, it's using the AST and you're given an AST. Though I'd prefer Zig macros. But anyways, so let's just copy this macro. Should I put it... I guess maybe, should we put it in the main code? It doesn't really matter, I think. But yeah, we could make it in our main code for now, maybe. There you go. So macro export, we create a declarative macro, not a procedural macro. The procedural macro is the more advanced one. The declarative macro kind of like does just substitution basically, but more advanced than that. It looks so weird. I don't know. I feel like C macros are better because it's simple and it's obvious to make complex stuff with them. Not really. Like, as I said, C macros just does string substitution. I'm just not familiar with the syntax and I didn't even try, honestly. But yeah. Anyways, so basically, let me try to figure it out. Yeah, I think it's kind of like functional programming to some degree, I think. Like if you were doing Haskell, maybe. So basically, if you have no arguments, right, to the print line macro here, you would do this. You would replace that macro with print macro, a new line. Where's the print macro though? Did we make it, or is it already given to us? Or hold on. Do we have a print macro? I don't know. Weird. Either way, we print a new line if no arguments given. if there is some arguments, I don't really understand the syntax correctly, but I think this is probably like either 0 times or more times. Actually, I'm not sure, but probably something like that. Like this one is get repeated multiple times, maybe. I'm not really familiar with Rust macros that much. Print format args, we use another macro here, and we pass in the arguments, I think. But anyway, that doesn't matter that much because we're just going to be using this. Macros are okay, so I think they're probably gonna actually explain this through or one or more rules. Yeah, so declarative macros at least are just rules. Though procedural macros, you actually get the AST and then you can do a transformation on that AST and you give it back to the compiler. So that's pretty crazy. Similar to match arms, the print line macro has 2 rules. The first rule is for invocations without arguments. Yeah, there you go. Print line, which is expanded to print new line and does just prints a new line. The second rule is for invocations with parameters such as print line hello or print line like this. It also expanded to an invocation, the print macro, passing all arguments and an additional new line at the end. Okay, so that's simple, although I'm not familiar with the syntax here. But the macro export attribute makes the macro available to the whole crate. Okay, not just the module is defined then. External crates also place the macro to crate root, which means we have to import the macro through use std print line instead of std macros print line. The parent macro is defined as, oh, so we are just creating the parent macro, or is it already created? I guess maybe let's find out, or maybe I have to use it first. Otherwise it wouldn't expand in the first place. So, okay. Oh, I'm already using the print macro. So, oh, what the heck? No, I'm actually changing the macro itself. Hold on, no, not what I wanted. Let's go to main rs, yeah, and here. So maybe instead of this, right? Maybe you want to use it. Print line, hello world. Oops. Would this work now? Okay, there you go. So print doesn't exist. So this is the print macro that we have used there. There you go. Again, you take all the arguments and use this crate IO print format args. Okay. And this macro expands to call the print function in the IO module. The crate variable ensures that the macro also works from outside the std crate by expanding to std when it's used in other crates. Huh? Okay, I see. The format args macro builds the fmt arguments type from the pass argument, which is passed to print. The print function libstd calls prints to, which is rather complicated because it supports different std out devices. We don't need that complexity since we just want to print to the VGA buffer. To print to the VGA buffer, we just copy the print line and print macros, but modify them to use our own print function. Okay, so we created a new function called print. We take fmt arguments. Okay, and we say writer.log.write fmt, and here we have the trait write, so we could use the write fmt function. It's given to us by the trait, and then we call the crate print macro. Okay, and then here the crate VGA buffer print. Makes sense. Let's just copy this. There you go. But we should probably put this in the VGA buffer. And there you go. Would this work now? Print line, would it work? There you go. Hello world with print line macro, finally. Okay, one thing that would change from the original is that we prefix the invocation to print macro with crate 2. Like the standard library, add a macro. Did I read this one? Note that this places the macro in the root namespace of the crate, so important than via does not work. Instead we have to use crate print line. Okay. looks our static writer and calls the write fmt method on this method is from the write tray. There you go, which we need to import. The additional unwrap at the end panics if print isn't successful. Okay, but since we always return okay and write stir, that should not happen. Yep, I see. Since the macros need to be able to call print from outside of the module, the function needs to be public. However, since we consider this a private implementation detail, the function needs to be public. However, since we consider this private implementation, we add the doc hidden attribute to hide it from the generated documentation. I see, cool. Doc hidden. So basically, since we have this doc hidden macro thing, right? It wouldn't be included in the documentation, pretty much. Now we can use println or star function. Great. Now that we don't have to import the macro in the main function because it already lives in the root namespace. And with that, we have re-implemented println without the standard library, without the Rust runtime, and without the C runtime. It's all in our operating system. Printing panic messages. Now that we have a println macro, we can use it in our panic function to print panic message and the location of the panic. Great. When we now insert some panic message in our start function, we get the following output. Panic, that's some panic message. And there you go, we got finally some error handling to some degree. Right, so we know not only the panic has occurred, but also the panic message and where in the code it happened. Great. Great, great, great. So we just call println info. Cool. Cool, cool, cool. Println info. Well, let's do it this way. There you go. Oops. And there you go. But hold on, we haven't tested panic yet. So let's test that. Panic. And now, instead of just, looping forever, we first of all print the panic message, panic.source main rs15.5, and then we loop again. Because we don't have halt yet. So we cannot stop the VM just yet. Or the OS. Anyways, printing panic messages, now insert. So in this post we learned about the structured VGA buffer and how it can be written through the memory map in an address. We created a Rust module that encapsulates the safety of writing this to the memory mapped buffer and presents a safe and convenient interface to the outside. Thanks to Cargo, we also saw how easy it is to add dependencies and third-party libraries. Yep. The two dependencies that we added, lazy static and spin, are very useful in OS development, and we will use them in more places in future posts. What's next? The next post explains how to set up Rust built-in test unit framework. We will then create some basic unit tests for the VGA buffer module from this post. Okay. Well, tests aren't that exciting. I'm not sure if I'm gonna continue today on this. Oh, IO ports. Cool. Serial ports. Interesting. Print an error message on panic. So until now we're basically just setting up Rust for operating system, for our own operating system, because we don't have a standard library. So serial print. And we're probably gonna set up here the serial port to be able to basically send data to our own machine from the VM. So we can do whatever we want with it in our own machine instead of the operating system. So like we could possibly, for example, make some code that does some stuff, output some bytes, and then we could possibly like display in an image in our own machine. But yeah. Anyways, it's basically used for debugging purposes. though modern computers doesn't contain them anymore. But of course we're using Chemio, which of course does have it. Port new, right, exit code. Yeah, I think it's probably enough for today. Let's keep some steam for now. And yeah, that was how much? 2 hours and 19 minutes or 20 minutes, say that. Yeah, that was very fun. That was the first video in our little operating system, I guess. And yeah, let's say well, for each I, right, and print line, or not print line, just print space, let's say I here, and cancel. Just making sure this works. And there you go. Okay, so yeah, great. Let's just add log, cargo toml, main rs, and VGA buffer. And yeah, so what we have done, VGA buffer and printing, I guess, or what does it call it? Hold on, VGA text mode. Okay, sure. VGA text mode. So commit, and let's push. Oh, hold on. Yeah, I need to pull my workflow and push. Cool. And yeah, that was it for the stream, guys. Thank you all for watching. And hello, Cubic. Welcome to my stream. Goodbye for now, guys. That was a lot of fun. And see you in the next one, maybe tomorrow. Goodbye.